Hi, in this lecture I'm going to be talking about the determinant, which is basically how we can map some square matrix to a single scalar value. This goes with chapter 2.11 of the Deep Learning textbook, so I suggest you read that after watching this lecture. The determinant usually holds quite a large place in introductory linear algebra courses just because it's quite a foundational aspect of linear algebra and is pretty complicated, so requires at least a few lectures to cover. But in this scenario, when we're talking about in the context of machine learning, determinants don't hold too much of a large place in the mathematics of machine learning, so I'll be just kind of squishing it all into one lecture and mostly talking about the geometric intuition and maybe offering one way to calculate them. So let's get to that. Alright, so let's start off with the geometric intuition for the determinant, just because that's really 90% of the battle in understanding what the determinant is and where these numbers come from. So I'm going to draw the Cartesian plane in 2 dimensions. Alright, so here's our coordinate plane. So what I'm going to do is I'm going to plot the 2 unit vectors on this plane. When I first introduced the term unit vectors, I used it to mean any vector of unit length, or a magnitude or norm of 1. But in this case, in this context, we often refer to, when we're talking about the unit vectors, we're often referring to 2 specific unit vectors. And those are the unit vectors that lie along the coordinate axes. More specifically, in this 2-dimensional case, those would be 1, 0, and 0, 1. So those would look like this. So this would be 1, 0, would go 1 in the direction of x, and y would go 1 in the direction of y. And those would be both unit vectors. Just a quick note on unit vectors. In 3 dimensions, we'd have three unit vectors, each going 1 in the direction of x, y, and z, and they'd look like this. Geometrically, you can understand them to look something like this is x, this is y, and this is z. So 1, 0, 0 would go a little bit in this direction, 0, 1, 0 would go a little bit in this direction, and 0, 0, 1 would go a little bit in this direction. Okay, that's all I just wanted to cover with the unit vector, just to kind of get that notation, that terminology down, I guess. Alright, so 0, 1, 0 and 0, 1 are here. Alright, so let's get some 2 by 2 matrix. And we'll get to the determinant shortly. 3, 1, 1, 1. So what we're going to do is we're going to see how we can find the geometric interpretation for this matrice's determinant. And the determinant of this matrix is 2, and I'll understand where we get that number from and what that number means later on. But that's just, I'm going to put that there for now and we'll explain it later. Okay, so what we're going to do is we're going to transform this coordinate space by the matrix 3, 1, 1, 2. I'm actually going to move this matrix up there because we're going to need this space over here. So I'm going to draw this over here. So 3, 1, 1, 2, that, and the determinant of that is 2. Alright, great. So what we're going to do is we're going to transform this coordinate plane by this matrix. So we're going to imagine every point in the space, so we're going to apply a linear transformation with this matrix. We're going to imagine every point in the space being multiplied by that matrix and showing up some other place and direction. So what we're going to do is we're going to transform this space, including these 2 vectors. So let's draw this transform space over here. Alright, so we have our transformed space right here. So let's plot these 2 vectors after undergoing this transformation and see what they look like after being transformed. Alright, so basically what we're going to do is we're going to multiply, let's take the unit vector in the x direction first, so 1, 0. So we're going to multiply 1, 0 by this matrix to see where it goes. Alright, so let's do that. So 1, 0. So this is going to equal sort of 3, 1, and 1, 0. So that's going to be 3 times 1 is 1, 3 times 1 is 3, 1 times 0 is 0. So that's going to be 3. And then 1 and 1, and 1 and 0, so 1 times 1 is 1, 1 times 0 is 0, so this is going to be 1. So 3, 1 is going to be right, this is going to be x of 3, so it's going to be going to right here. So you can notice that after undergoing that transformation, that x vector goes quite a long way, it goes over here. Alright, so now let's transform the y unit vector, so 0, 1. And see what happens to this guy. So we're going to do 3, 1, and 0, 1. So 3 times 0 is 0, 1 times 1 is 1. So the first thing is going to be 1. And 1 times 1 times 1 times 0 is 0, and 1 times 1 is 1. So it's going to be 1 again. So this vector is going to go to 1, 1. That's a bit inaccurate. All right. Notice here that the unit vector 1, 0 went exactly to what this first column was. So 1, 0 went to 3, 1, And notice that the second unit vector, 0, 1, went straight to where the second column is at, 1, 1. So you can actually think of a matrix as encoding where the unit vectors go after undergoing that transformation. So that's just a quick little trick that we can use later on. Okay, so what we're going to do to actually understand what the determinant means is we're going to look at the area of the parallelogram spanned by these two pairs of vectors. All right, so what we're going to do, so let's make the parallelogram that these two vectors create that looks something like this, like that. And then we'll find the area of this parallelogram. So this area of this parallelogram, so this area here. So this is going to be a 1 by 1 area, so this is going to be 1 by 1. So the area of this square is going to be 1. Now let's do something a little trickier. Let's look at the area of the parallelogram created by these two vectors. And first we have to actually see what is the parallelogram created by these two vectors. So I can imagine this vector here being the left and right side. So let's move this over here. Right, roughly, and this becomes the top side of it. So roughly, the parallelogram created by those two vectors will look something like that. So let's find the area of this. And although it's a pain to measure what that area actually is, I can instantaneously say the area of that shape is 2. And the reason I know that is from the determinant and the geometric understanding of the determinant. So the geometric understanding of the determinant is the determinant tells you how much area scales after undergoing this linear transformation 3, 1, 1, 1. So before we had an area of 1. So these same vectors get, transformed to these vectors over here. So the area spanned is scaled by the multiple of the determinant. So we multiply 1 by the determinant to get the resulting area, which is 2. It's a property of linear transformations that the scaling of area is the same everywhere. So if we had some area over here, so say we had some area like some circle over here, and you can understand a circle, the circumference of the circle just being a lot of little vectors, a lot of little points in a circle, right? So you can imagine after undergoing a transformation, all the vectors that make up the circumference will be stretched and squished in some sort of way over here, and we'll end up with a slightly wider circle. And this circle will also be 2 times the area of this circle. So it goes that any area in this coordinate plane will be multiplied by 2, multiplied by the determinant, scaled by the determinant after undergoing the transformation. So the determinant just tells us how area scales after undergoing this transformation. Let's take another pair of vectors. I'm not going to actually give numbers this time. Let's just do it kind of theoretically. So say we have a vector going like this, and let's say we have a vector that goes like this. So the area, the parallelogram spanned by these two looks something like this. Right? So then the area of this parallelogram, let's say it's maybe 12. Say the area of this is 12. So let's plug these two vectors into this linear transformation and say they look really wonky and weird. They look something like maybe this, and maybe something like this. Right? So after undergoing the transformation, they begin to look like that. They actually kind of look parallel, which is misleading, so let's not make them parallel. So it looks something like this maybe, curves, but you can't achieve perfection. Something like that, right? So you can understand that the area of the parallelogram created by these two vectors, these two very narrow vectors like this, the area created by these two vectors here will be 2 times this area. So this will be 24 units, square units. So that's what the determinant means. It just tells us how area scales after undergoing some linear transformation. All right. Now let's look at a few special cases when the determinant equals some certain value. So first let's look at when the determinant equals 1. And then after all this, I'll tell you actually how we calculate the determinant. So let's say the determinant is equal to 1. And I won't tell you how we calculate it, but let's say a vector that would a matrix that would have the determinant of 1, which is something that would look like this maybe. So that would have a determinant of 1. And if we kind of imagine geometrically, I won't go through an example just because we don't have enough time, but if you can imagine geometrically, a matrix with determinant 1 does not change the areas. does not stretch or scale the areas after undergoing some sort of transformation. So you can think back to our lecture in SVD and how we learned that orthogonal matrices, so orthogonal matrices Q, do not change or stretch space. They just rotate space. If you think of an orthogonal matrix as a linear transformation, they just rotate space. So then logically you can think that orthogonal matrices have a determinant of 1, but they don't stretch or scale space. Okay, so that's just one quick note I wanted to make. Let's say what happens when the determinant equals 0. And this is an interesting case, and I'll actually I'll do an example with this one. So I'll write out a matrix with determinant 0. So that'd be something like 2, 4, 1, 2. And I'm going to raise this board, and while I raise this board, you can think about what you think this means geometrically. Alright, so hopefully you're done thinking now. So what we're going to do, again, is we're going to take this matrix here, this example matrix, and we're going to transform our entire space now this time by this matrix and see the transformed space in this Cartesian plane. So we're going to start with these unit vectors and see how these unit vectors transform. So we're going to multiply these unit vectors by this matrix. Let's erase this. And using our trick that we learned last time, that the x unit vector, so 1, 0, simply becomes the first column, 2, 4. Let's put that in. So 2, 4, that's going to be right here. And let's do this in green actually. So 2, 4 is going to be right about here. So let's write that vector. So that's going to be where our x unit vector goes. And now let's plug our y vector in for that, and you remember that our trick tells us the second column of this matrix is where our y unit vector 0, 1 goes. So this goes to 1, 2. So that's easy to plot. So 1, 2 is going to be right here. Alright, so notice, once I get out of the way, notice that these two vectors are collinear. So you can imagine that while undergoing this transformation, you can have this image in your head that these two vectors stretch and then kind of converge to be on the same line, and then you can see that they're on the same line here. And we can kind of think of the area thing, right? So the determinant, the area of this parallelogram here is 1 still, but after undergoing this transformation, the area of this resulting space is 0, because the area of a line is 0. And since linear transformations have to be consistent everywhere, so some circle, I guess the same circle over here, would have to kind of become a line over here, because all areas in this space have to be scaled equally, doesn't matter where you are in this plane, they have to be scaled equally. So that means everything here will become a line, and more specifically, it'll actually go onto this same line. For example, if we multiply an example, say we have an example, maybe, thinking of a good example, maybe 2, 0. We have the matrix 2, 0. So that's right here. Let's do this in red. We have the matrix, we have the vector 2, 0. So that's right here. So let's see where 2, 0 goes, undergoing the same transformation. So 2, 0. So we multiply this first row by that, so it's going to be 4. So our x is going to be 4. I'm going to multiply this by this, and we're going to get 8. So our resulting thing has a x of 4 and a y of 8. So x of 4, and we have to actually add 2 more things here. So let's say this is our 7, and this is our 8. So an x of 4 and a y of 8 takes us from here up to about here, right? About there. So you can see roughly that this point is also in the exact same line, the exact same span as these vectors here. And you can imagine that every single point in this entire coordinate space, so every single vector, you can think of all the possible vectors in this entire space, gets squished into a single line here. So every vector gets transformed onto the same line. And that's what happens, that's what you can imagine when the determinant is equal to 0, that this entire space squishes onto a single line after undergoing the transformation. And you can also notice that it makes a lot of sense that this matrix has linearly dependent columns. And you can kind of maybe work through that yourself to understand maybe why that makes sense, or why that makes a little sense. That matrices with determinant 0 are the same matrices that have dependent columns and are thus uninvertible. Sorry. Okay, so now that we're done with that, I want to give a quick intuition about how we can calculate determinants. Before quickly talking about how we can actually compute the determinant of any matrix A, it's very quick and very important to quickly mention how we do notation for the determinant. So if we have some matrix A, we can display its determinant in two main ways. We can say det of A, and we can sometimes use this, where we just put two bars around the A. These both equal the determinant of A. So that's just a quick thing to clarify. All right, so to finish up this lecture, I'm going to talk about how we can calculate the determinant for any size square matrix A. There's a few quick tricks that you can use to calculate smaller matrices determinants, like 2 by 2 and 3 by 3, but since in machine learning we often deal with large matrices, these tricks quickly become pretty irrelevant. So let's look at the general way to calculate the determinant. So if we have any size matrix A, we can calculate its determinant by taking a product of all of its eigenvalues. So let's see why that works. Let's give a geometric intuition as to why. So say A is some 2 by 2 matrix, meaning that it has two eigenvectors and two eigenvalues. And furthermore, let's say A is symmetric, so these eigenvectors are going to be orthogonal to each other. So let's plot these eigenvectors. So I say that's eigenvector 1, and that's eigenvector 2. These are right angled to each other. So let's say this is V1. Let's not put that in the way there. We say this is V1, and say this is V2. But more importantly, let's give the actual lengths of these vectors. So say this is A units long, and this is B units long. So now what we're going to do is we're going to look at the area of the parallelogram formed by these two vectors here. So the parallelogram will look something like this, roughly. And since the side lengths of this parallelogram are A and B, the area of this thing is going to be A times B, AB. So the area of this rectangle formed by these two vectors is AB. So if these two vectors are indeed the eigenvectors, if we transform this space by A, these eigenvectors shouldn't move. They should just stretch and squish along their same axes depending on their eigenvalue. So since these are the eigenvectors, let's transform the space, meaning that each of these gets stretched and scaled by their corresponding eigenvalue. So let's say V1's eigenvalue is quite large, so our resulting vector is going to be quite long. Say something like that. So this is going to be our new vector, which is going to be V1 times lambda 1, but more importantly, the length of this new vector will be lambda 1 times A. And then let's look at this one. So now let's say this only gets scaled a little bit. So this new vector is going to be lambda 2 times V2, but more importantly, it'll have a length of B, lambda 2. So now let's look at the area of the parallelogram created by these two new vectors. All right. So this is some rectangle or parallelogram, and the side lengths of this new one are lambda 1a and lambda 2b. So the area of this new parallelogram will be lambda 1a times lambda 2b, which will be a, b, lambda 1, lambda 2. So notice we can find the scaling factor of these two areas. This larger area is simply the old area AB multiplied by lambda 1, lambda 2. So the scaling factor from this area to this area is multiplying this area by lambda 1 times lambda 2. And since a main property of linear transformations is that the scaling of area is the same everywhere, then any two vectors or any area spanned by vectors in this entire space will be scaled by the exact same constant. And this constant is the product of the eigenvalues. And remember that the geometric understanding for the determinant of some matrix is the scaling factor of areas. So the determinant of A is the product of the eigenvalues. Hopefully that makes sense. That was a bit of a long lecture, but there's a lot of things that need to be talked about, and hopefully that sums it up pretty nicely. And that's how we calculate the determinant of any matrix. So I'll see you in the next lecture, which will hopefully be in the next unit. See ya!